Welcome back everyone to Data Science for Everyone. Today we're going to be looking at recursive least squares with stats models. Let's get started. So previously we looked at data revolving around the copper industry. Today we're going to be looking at the quantity theory of money. Now the quantity theory of money suggests that a given change in the rate of change in the quantity of money induces an equal change in the rate of the price of inflation. So this is from Lucas in 1980. Now, following the Lucas's suggestions, we're going to examine the relationship between the double-sided exponentially weighted moving averages of money growth and the CPI. So inflation specifically. So although Lucas found that the relationship between these variables is stable, more recently though it appears that the relationship is unstable. So let's go on and get started with this. Now we have our standard imports that we've had before. Now the next thing that we're going to want is the pandas data reader .data import data reader. Now a lot of you guys probably know that this particular package is very temperamental, particularly when it comes to getting a lot of stock data. However, when it comes from getting data from Fred, the Federal Reserve in St. Louis, it's actually still doing quite strong. So go on and import that as well. If you need to pip install it. And so let's go on and do something like start date. In here is going to be, we want 1959-12-01. Our end date in here will be, let's do 2015-01-01. Our M2 data is going to be data reader M2SL, and this is going to be from the Fred, the Federal Reserve in St. Louis. Start is equal to start, end is equal to end. And we'll do this again, but we'll do it for CPI, is equal to our data reader, and this is going to be CPIAU CSL, again from Fred. Start is equal to start, end is equal to end, and we'll go on and run this. Now we need to go on and, whoops, what didn't it like here? What did I misspell? Let me double check here. Go up. Whoops, right here. There should be an A. There we go. So we need to actually go on and we're going to create up in here a function for exponentially weighted moving averages. So exponentially weighted moving averages. So we're going to actually, let's go on and actually create that up. So def EWMA. Here it's going to take a series. It's going to take a beta. It's going to take an in window. And then let's go on and say our number of observations is equal to the length of the series. Some scalar is going to be 1 minus beta divided by 1 plus beta. Then we'll have our moving average is going to be some list here. K is equal to mp.a range in here in window, so how big our window is. Window, from 0 to -1. Our weights in here are going to be mpr underscore, and then here we'll have a beta to the k. 1 beta to the k, and we need to reverse this list here. For t in range in here, and we want in window, number of observations minus our in window. The window itself is going to be equal to the series dot iloc. We need to grab the location of t minus in window all the way up through t plus in underscore window plus 1. Dot values, because we actually need the values of that itself. Ma dot append in here, we want our scalar. multiplied by our MP dot, the sum of the weights, multiplied by the window. Then we're going to want to return, in this instance, another series. In here, MA name is equal to the series dot name. Here, the index is going to be equal to our series dot iloc here, and we want our in window all the way through negative of our in window dot index. Okay, and let's go on and run that. And I need to double check. I'm hoping that that's correct. Let's double check real quick. I'm going to just go through it real quick, and then I'll be right back. Okay, everything looked correct. So let's go on and actually run a quick example in here. So we want our M2 EWMA is going to be EWMA np.log of our M2, and we want the M2 SL variable, and we need to resample this to quarterly. And we want the mean of that. Let me double check on, let me move this up a little bit. Resample, quarterly, mean, and then we need the difference. .iloc in here of starting at 1 all the way to the end. And then we need in here, the beta needs to be 0.95. So that's our beta filter from Lucas. Okay, and we want a 10-year window. So a 10-year quarterly window. So we need to multiply that by 4. And I think that's good for that one. So then let's also do in here, we'll do the same thing. I'm actually just going to go on and copy this and put it down here. And we're going to change this to CPI of our CPI with CPI AUCSL. With everything else will be the same. Okay, so let's run that. And then we also want in here to actually go on and plot this. And we'll plot this, let's see, well let's just kind of show you, and then we can talk about it for a second. So fig axis is equal to plt.subplots. Fig size is equal to, let's do a 15 by 5. Axis 1 will be plot M2 EWMA. Label is equal to our money growth, EWMA. Then the next axis is going to be dot plot, and that's CPI EWMA. Label in here is going to be CPI inflation, EWMA. And then axis.legend. Run that. Okay, and now we can actually see here, you see this nice little bit of a curve in here as it's gone down, okay? Now, basically, everything seems to be moving together, okay, up until about the 90s. That's around right here. And then you notice here that they definitely start to deviate after that. Okay, so that's where everything kind of seems to go out of whack with the Lucas model. So let's go on and actually run this with our recursive least squares model and see what we can find. So our endogenous is going to be our CPI EWMA. Our exogenous is going to be our SM.add constant. in here are M2 EWMA. Our model itself is going to be our sm.recursive. Least squares model with our endogenous and our exogenous. Our results here is going to be our model.fit. And then let's go on and look at our summary. Okay, 140 observations. R squared is 0.18. Let's go on and actually plot this as well to see what we can see here. And so we'll do something like res.plot, recursive, and remember we want the coefficients. Coefficient 1 alpha is equal to none. Oh, and I want to put that there. Okay, and we can see that everything's going okay. There's definitely a dip in the late 70s, and again it drops down again whenever we look at the 90s. Okay, so again there's definitely substantial deviation. Now let's actually see when we look at the cumulative sum to show how there's going to be definitely a substantial deviation. All right, so this is okay. This kind of gives us an idea that there's definitely something happening. Okay, particularly around here and here. But let's look at our cumulative sum plot. Res.plot cumulative sum here, and you can see, whoa, it definitely starts deviating. Okay, so it's in there up until around, let's say 82 maybe, and then it definitely starts going sideways. Now let's take a look at that with the cumulative sum squares model and see how it deviates there as well. So let's do something like res.plot cum sum squares. Let's take a look. So again, we see the same thing happening now, but this is definitely happening a little bit earlier. This is in the late 70s, and then it just stays out. Okay, so if we take that look back again here, notice, so basically around that late 70s mark that we're seeing that deviation with the recursive estimates is definitely going to be matching up to where everything starts going wonky again. Now notice though, it does start going back in the early 2000s, so maybe things got better and got back in shape. I don't know. We can maybe use that to speculate, and maybe we can take the same type of data and look at it from maybe 04 all the way up to the 2020 time frame, okay, where we're in now. So if you guys like this, please comment, subscribe, and hit that like button, and I will see you guys next time. Bye-bye.